Nature is not only more subtle than we suppose, but more subtle than we can suppose. Albert Einstein. Please watch to the end. The most interesting part is at the very end. Euplectella aspergillum, commonly known as Venus flower basket, is a deep-sea glass sponge belonging to the class Hexactinellida. It inhabits bathyal and abyssal depths of the western Pacific, where sunlight never penetrates and physical disturbance is minimal. Unlike animals that rely on movement or aggression, this species survives through structural perfection and passive efficiency. The body of Euplectella aspergillum is cylindrical and composed almost entirely of silica. Its skeleton forms an intricate lattice of interlocking spicules arranged in precise geometric patterns. This structure is not accidental. It provides exceptional strength while remaining lightweight, allowing the sponge to withstand pressure and deep-sea currents without collapsing. One of the most remarkable aspects of this species is how its skeleton manages mechanical stress. The lattice is built from hierarchical layers of silica fibers fused at specific angles. This design distributes force evenly across the structure, preventing fractures from propagating. Engineers often cite Euplectella aspergillum as a natural example of optimized load-bearing architecture. An exclusive anatomical detail rarely emphasized outside materials science research concerns the nanoscale composition of its spicules. Each silica fiber contains alternating organic and inorganic layers. This layered construction increases toughness and crack resistance far beyond what pure glass would provide. In effect, the sponge produces a biological composite material superior to many synthetic equivalents. Euplectella aspergillum is a suspension feeder. Water flows through numerous small openings in the lattice, carrying microscopic organic particles and bacteria. Specialized cells capture this material and transport nutrients throughout the body. Because food availability in the deep sea is limited, the sponge's filtration system is optimized for continuous, low-energy operation. The sponge anchors itself to soft sediment using long, flexible basal spicules that act like root fibers. These structures secure the sponge upright, elevating it above the seafloor and improving access to water currents. This elevation also reduces sediment clogging, a critical factor for survival in fine-grained deep-sea environments. A well-known but biologically grounded aspect of Euplectella aspergillum is its association with small shrimp. Juvenile shrimp can enter the lattice when young, but as they grow, escape becomes impossible. The sponge thus becomes both habitat and lifelong enclosure. While often romanticized, this relationship reflects a real ecological interaction in which shelter is exchanged for cleaning and waste recycling. Reproduction involves the release of larvae into the water column. These larvae eventually settle on the seafloor, where they begin constructing their silica skeleton from dissolved silicon in seawater. This process requires precise biological control, as silica deposition must follow exact geometric rules to produce a functional lattice. Euplectella aspergillum demonstrates that survival in extreme environments does not require speed, intelligence, or aggression. Instead, it relies on stability, structure, and efficiency perfected over millions of years. In evolution, what persists is not what is strongest, but what is most stable. Stephen J. Good. If this changed your understanding of deep-sea life, please support the channel. Like the video, subscribe, share it, and tell us in the comments which extraordinary deep-sea organism you'd like to explore next. Let's discuss in the comments.